I will tell you in 5 lectures the chemical history of a candle. There is not a law under which any part of the universe is governed which does not come into play and is touched upon in the chemistry of a candle. There is no better, there is no more open door by which you can enter into the study of science than by considering the physical phenomena of a candle. I trust, therefore, I shall not disappoint you in choosing this for my subject rather than any newer topic which could not be better were it even so good. So, now as to the light of the candle. Notice that when the flame runs down the wick to the wax, it gets extinguished, but it goes on burning in the part above. Now, I have no doubt you will ask, how is it that the wax, which will not burn of itself, gets up to the top of the wick where it will burn? We shall presently examine that, but there is a much more wonderful thing about the burning of a candle than this. You have here a solid substance, the fuel, with no vessel to contain it. And how is it that this can get up to the place where the flame is? How is it that this solid gets there, it not being a fluid? Or when it's made of fluid, then how is it that it keeps together? This is a wonderful thing about a candle. You see that a beautiful cup is formed. As the air comes to the candle, it moves upwards by the force of current which the heat of the candle produces. And it so cools all the sides of the wax as to keep the edge much cooler than the part within. The part within melts by the flame that runs down the wick as far as it can go before it's extinguished, but the part on the outside does not melt. The same force of gravity which holds worlds together holds this fluid in a horizontal position, and if the cup be not horizontal, of course the fluid will run away in guttering. You see, therefore, that the cup is formed by this beautifully, regularly ascending current of air playing upon all sides, which keeps the exterior of the candle cool. No fuel would serve for a candle which has not the property of giving this cup. These beautiful candles, which are irregular and intermittent in their shape, cannot have that nicely formed edge to the cup, which is the great beauty in a candle. I hope you will now see that the perfection of a process, that is its utility, is the better point of beauty about it. It is not the best looking thing, but the best acting thing, which is the most advantageous to us. These good looking candles are bad burning ones. There is guttering because of the irregularity of the stream of air and the badness of the cup which is formed thereby. You may see some pretty examples, and I trust you will notice these instances of the action of the ascending current when you have a little gutter running down the side of a candle, making it thicker there than it is elsewhere. As the candle goes on burning, that keeps its place and forms a little pillar sticking up by the side because as it rises above the rest of the fuel or wax, the air gets better around it and it is more cooled and better able to resist the action of the heat at a little distance. Now, the great mistakes and faults with regard to candles, as in many other things, often brings with them instruction which we should not receive if they had not occurred. We come here to be scientists, and I hope you will always remember that whenever a result happens, especially if it be new, you should say, what is the cause? Why does it occur? And you will in the course of time find out the reason. Then there is another point about these candles which will answer a question, that is as to the way in which the fluid gets out of the cup, up the wick, and into the place of combustion. You see that the flames on these burning wicks do not run down to the wax and melt it all away, but keep to their own right place. They are fenced off from the fluid below and do not encroach on the cup at the sides. I cannot imagine a more beautiful example than the condition of adjustment under which a candle makes one part subserve to the other to the very end of its action. A combustible thing like that, burning away gradually, never being intruded upon by the flame, is a very beautiful sight. Especially when you come to learn what a vigorous thing flame is, what power it has of destroying the wax itself when it gets hold of it, and of disturbing its proper form if it comes only too near. But how does the flame get a hold of the fuel? Capillary action conveys the fuel to the part where combustion goes on, and it is deposited there not in a careless way, but very beautifully in the very midst of the center of action which takes place around it. Now, I'm going to give you 2 instances of capillary action. It is that kind of action or attraction which makes 2 things that do not dissolve in each other still hold together. When you wash your hands, you take a towel to wipe off the water, and it is by that kind of wetting or that kind of attraction which makes the towel become wet with water that the wick is made wet with the wax. If you throw the towel over the side of the basin, before long it will draw the water out of the basin like the wick draws the wax out of the candle. Let me show you another application of the same principle. You see this hollow glass tube filled with table salt. I'll fill the dish with some alcohol colored with red food coloring. You see the fluid rising through the salt. There being no pores in the glass, the fluid cannot go in that direction, but must pass through its length. Already the fluid is at the top of the tube. Now I can light it and make it serve as a candle. The fluid has risen by the capillary action of the salt, just as it does through the wick in the candle. Now, the only reason why the candle does not burn all down the sides of the wick is that the melted wax extinguishes the flame. You know that a candle, if turned upside down so as to allow the fuel to run upon the wick, will be put out. The reason is that the flame has not had time to make the fuel hot enough to burn as it does above, where it is carried in small quantities into the wick and has all the effect of the heat exercised upon it. There's another condition which you must learn as regards the candle, without which you would not be able fully to understand the science of it, and that is the vaporous condition of the fuel. In order that you may understand that, let me show you a very pretty experiment. If you blow a candle out carefully, you'll see the vapor rise from it. You have, I know, often smelt the vapor of a blown out candle, and a very bad smell it is. But if you blow it out lightly, you'll be able to see pretty well the vapor into which this solid matter is transformed. When I hold a lighted match 2 or 3 inches from the wick, you can observe a train of fire going through the air till it reaches the candle. I'm obliged to be quick and ready because if I allow the vapor time to cool, it becomes condensed into a liquid or solid, or the stream of combustible matter gets disturbed. Now, to the shape or form of the flame. It concerns us much to know about the condition which the matter of the candle finally assumes at the top of the wick, where you have such beauty and brightness as nothing but combustion or flame can produce. You have the glittering beauty of gold and silver, and the still higher luster of jewels like the ruby and diamond. But none of these rival the brilliancy and beauty of flame. What diamond can shine like flame? It owes its luster at night time to the very flame shining upon it. The flame shines in darkness, but the light which the diamond has is as nothing until the flame shine upon it when it is brilliant again. The candle alone shines by itself and for those who have arranged the materials. The flame is a bright oblong, brighter at the top than toward the bottom, with the wick in the middle. And besides the wick in the middle, certain darker parts toward the bottom where the ignition is not so perfect as in the part above. Now, let me show you. There's a matter rising about it which you do not see. You can actually see streaming round the flame something which is not part of the flame, but is ascending and drawing the flame upwards. There is a current formed which draws the flame out, for the flame which you see is really drawn out by the current and drawn upward to a great height. How remarkable it is that the thing which is light enough to produce shadows of other objects can be made to throw its own shadow. You observe the shadow of the candle and of the wick. Then there is a darkish part, and then a part which is more distinct. Curiously enough, however, what we see in the shadow as the darkest part of the flame is in reality the brightest part. And here you see streaming upward the ascending current of hot air, which draws out the flame, supplies it with air, and cools the sides of the cup of melted fuel. You know the flame goes up or down according to the current. You see then that we have the power in this way of varying the flame in different directions. Many of the flames you see here vary in their shape by the currents of air blowing around them in different directions. But we can, if we like, make flames so that they look like fixtures, and we can photograph them. Indeed, we have to photograph them so that they become fixed to us if we wish to find out everything concerning them. If I take a flame sufficiently large, it does not keep that homogeneous, that uniform condition of shape, but it breaks out with a power of life which is quite wonderful. In what way does it differ from an ordinary candle? It differs very much in one respect. We have a vivacity and power about it, a beauty and a life entirely different from the light presented by a candle. You see those fine tongues of flame rising up. You have the same general disposition of the mass of the flame from below upwards, but in addition to that, you have this remarkable breaking out into tongues which you do not perceive in the case of a candle. Now, why is this? You have the air creeping in over the edge of the dish forming these tongues. Why? Because through the force of the current and the irregularity of the action of the flame, it cannot flow in one uniform stream. The air flows in so irregularly that you have what would otherwise be a single image broken up into a variety of forms, and each of these little tongues has an independent existence of its own. Indeed, I might say you have here a multitude of independent candles. You must not imagine, because you see these tongues all at once, that the flame is of this particular shape. A flame of that shape is never so at any one time. Never is a body of flame like that which you just saw rising from the ball of the shape it appears to you. It consists of a multitude of different shapes, succeeding each other so fast that the eye is only able to take cognizance of them all at once. They do not occur all at once. It is only because we see these shapes in such rapid succession that they seem to us to exist all at one time. We have thus far spent our time considering the light of the candle, discussing how the fuel gets to the wick and the form of the flame upon combustion. But we have more questions to ponder. From where does the brightness come? And where does the candle eventually go? And in a larger sense, how do the products of combustion lead us to a discussion of the atmosphere? And what is the relationship between combustion and respiration? I started this lecture by claiming that there is no more open door by which to enter into the study of science than by considering the physical phenomenon of the candle. Over the next 4 lectures, I hope to prove this to you. We were occupied the last time we met in considering the general character and arrangement as regards the fluid portion of a candle and the way in which that fluid got into the place of combustion. And now I have to ask your attention to the means by which we are enabled to ascertain what happens in any particular part of the flame, why it happens, what it does in happening, and where, after all, the whole candle goes to. Because, as you know very well, a candle being brought before us and burned disappears, if burned properly, without the least trace of dirt in the candlestick. And this is a very curious phenomenon. We will examine this dark part first. And now I take this bent glass tube and introduce one end into the middle of the flame. You see at once that something is coming from the flame. At the other end, you will see that something from the middle part of the flame is gradually drawn out and goes through the tube and into that flask, and there behaves very differently from what it does in the open air. It not only escapes from the end of the tube, but falls down to the bottom of the flask like a heavy substance, as indeed it is. We find that it is the wax of the candle made into a vaporous fluid, not a gas. You must learn the difference between a gas and a vapor. A gas remains permanent, a vapor is something that will condense. If you blow out a candle, you perceive a very nasty smell, resulting from the condensation of this vapor. This is very different from what you have outside the flame. And in order to make that more clear to you, I'm about to produce and set fire to a larger proportion of this vapor. For what we have in the small way in a candle, to understand thoroughly, we must as scientists produce in a larger way if needful, that we may examine the different parts. Here is some wax in a glass flask, and I've made it hot as the inside of that candle flame is hot and the matter about the wick is hot. You see that the wax has become fluid and there's a little smoke coming from it and vapor rising up that I can set on fire. This then is exactly the same kind of vapor as we have in the middle of the candle. I have arranged another tube carefully in the flame, and I was able, by a little care, to get that vapor to pass through the tube to the other extremity, where I will light it and obtain absolutely the flame of the candle at a place distant from it. Now, look at that. Is not that a very pretty experiment? And you see from this that there are clearly 2 different kinds of action. One, the production of the vapor, and the other, the combustion of it, both of which take place in particular parts of the candle. I shall get no vapor from that part which is already burnt. If I raise the tube to the upper part of the flame, so soon as the vapor has been swept away, what comes away will be no longer combustible. It is already burned. How burned? By burned thus. In the middle of the flame where the wick is, there is this combustible vapor. On the outside of the flame is the air which we shall find necessary for the burning of the candle. Between the 2, intense chemical action takes place, whereby the air and the fuel act upon each other, and at the very same time that we obtain light, the vapor itself is consumed. If you examine where the heat of a candle is, you'll find it very curiously arranged. Suppose I take this candle and hold a piece of paper close up on the flame. Where is the heat of that flame? Do you not see that it is not in the inside? It is in a ring exactly in the place where I told you the chemical action was. And even in my irregular mode of making this experiment, if there is not too much disturbance, there will always be a ring because the heat is where the air and the fuel come together. This is most important for us as we proceed with our subject. Air is absolutely necessary for combustion. And what is more, I must have you understand that fresh air is necessary, or else we should be imperfect in our reasoning and our experiments. Here is a jar of air. I place it over a candle, and it burns very nicely in it at first, showing that what I have said about it is true, but there will soon be a change. See how the flame is drawing upwards, presently fading, and at last going out. And going out why? The jar is full of air, partly changed, partly not changed, but it does not contain sufficient of the fresh air which is necessary for the combustion of a candle. These are all points which we, as young chemists, have to gather up. And if we look a little more closely into this kind of action, we shall soon find certain steps of reasoning extremely interesting. We have the case of the combustion of a candle, we have the case of a candle being put up by the want of air, and we now have the case of imperfect combustion. And this is to us so interesting that I want you to understand it as thoroughly as you do the case of a candle burning in its best possible manner. I will now make a great flame because we need the largest possible illustration. Here is a larger wick made from these cotton balls. All these things are the same as candles after all. If we have larger wicks, we must have a larger supply of air or we shall have less perfect combustion. Now, look at the black substance going up into the atmosphere. There's a regular stream of it. Look at the soot that flies off from the flame. See what an imperfect combustion it is because it cannot get enough air. What then is happening? Why, certain things which are necessary to the combustion of a candle are absent, and very bad results are accordingly produced. But we see what happens to a candle when it is burnt in a pure and proper state of air. Recall the charred ring on the paper. And on the other side, you see the burning of a candle produces the same kind of soot, charcoal, or carbon. Let me explain to you, as it is quite necessary for our purpose, that although I take a candle and give you as the general result its combustion in the form of a flame, we must see whether combustion is always in this condition or whether there are other conditions of flame. And we shall soon discover that there are, and that they are most important to us. Here is a little gunpowder. You know that gunpowder burns with flame. We may fairly call it flame. It contains carbon and other materials which altogether cause it to burn with a flame. And here is some pulverized iron or iron filings. Now, I propose burning these two things together, my object being to make the gunpowder set fire to the filings and burn them in the air, and thereby show the difference between substances burning with flame and not with flame. Now, here is the mixture, and when I set fire to it, you must watch the combustion, and you will see that it is of two kinds. You will see the gunpowder burning with a flame and the filings thrown up. You will see them burning too, but without the production of flame. They will each burn separately. There is the gunpowder which burns with a flame, and there are the filings. They burn with a different kind of combustion. You see then these two great distinctions, and upon these differences depend all the utility and all the beauty of flame which we use for the purpose of giving off light. When we use oil or gas or candle for the purpose of illumination, their fitness all depends on these different kinds of combustion. There are such curious conditions of flame that it requires some cleverness and nicety of discrimination to distinguish the kinds of combustion one from another. For instance, here is a powder which is very combustible, consisting, as you see, of separate little particles. It is called lycopodium, and each of these particles can produce a vapor and produce its own flame. But to see them burning, you would imagine it was all one flame. I will now set fire to a quantity, and you will see the effect. We saw a cloud of flame, apparently in one body, but that rushing noise was proof that the combustion was not a continuous or a regular one. This is not an example of combustion like that of the filings I had been speaking of, to which we must now return. Suppose I take a candle and examine that part of it which appears brightest to our eyes. Why? There I get those black particles, which already you have seen many times evolve from the flame, and which I am now about to evolve in a different way. I have arranged the glass tube so as just to dip into this luminous part, as in our first experiment, only higher. You see the result. In place of having the same white vapor that we had before, we now have a black vapor. There it goes, as black as ink. It is certainly very different from the white vapor, and when we put a light to it, we shall find that it does not burn. Well, these particles, as I said before, are just the smoke of the candle. Why, it is the same carbon which exists in the candle. And how comes it out of the candle wax? It evidently existed in the wax, or else we should not have had it here. And now I want you to follow me in this explanation. You would hardly think that all those substances which flew around London in the form of soots and blacks are the very beauty and life of the flame, and which are burned as those iron filings were burned. I want you now to follow me in this point, that whenever a substance burns, as the iron filings burnt in the flame of gunpowder without assuming the vapor state, whether it becomes liquid or remains solid, it becomes exceedingly luminous. What I have to say is applicable to all substances, whether they burned or whether they do not burn, that they are exceedingly bright if they retain their solid form, and that it is to this presence of solid particles in the candle flame that it owes its brilliancy. I have here a piece of carbon or charcoal which will burn and give us light exactly in the same manner as if it were burnt as part of a candle. The heat that is in the flame of a candle decomposes the vapor of the wax and sets free the carbon particles. They rise up heated and glowing as this now glows, and then enter into the air. But the particles, when burnt, never pass off from a candle in the form of carbon. They go off into the air as a perfectly invisible substance. I shall tell you about this later. Is it not beautiful to think that such a process is going on, and that such a dirty thing as charcoal can become so incandescent? You see, it comes to this, that all bright flames contain these solid particles. All things that burn and produce solid particles, either during the time they are burning, as in the candle, or immediately after being burnt, as in the case of the gunpowder and iron filings, all these things give us this glorious and beautiful light. I've mixed potassium, chlorate, and sugar. I shall touch them with a drop of sulfuric acid for the purpose of giving you an illustration of chemical action, and they will instantly burn. Now, from the appearance of things, you can judge for yourselves whether they produce solid matter in burning. I've given you the train of reasoning which will enable you to say whether they do or do not. For what is this bright flame but the solid particles passing off? When the particles are not separated, you get no brightness. The flame of a candle owes its brightness to the separation during combustion of these particles of carbon. I can very quickly alter that arrangement. Here, for instance, is a bright yellow flame from propane in a Bunsen burner. Supposing I add so much air to the flame as to cause all to burn before those particles are set free, I shall not have this brightness. There is plenty of carbon in the gas, but because the atmosphere can get to it and mix with it before it burns, you see how pale and blue the flame is. The difference is solely due to the solid particles not being separated before the gas is burnt. You observe that there are certain products as the result of the combustion of a candle, and that of these products, one portion may be considered as charcoal or soot. That charcoal, when afterwards burnt, produces some other product, and it concerns us very much now to ascertain what that other product is. This vessel captures all the products of the candle, and you will presently see the vessel's walls become quite opaque. The sides of the jar become cloudy, and the light begins to burn feebly. It is the products you see which make the light so dim, and this is the same thing which makes the sides of the vessel so opaque. If I take a spoon that's been in cold water, wipe it dry, and hold it over a candle so as not to soot it, you will find that it becomes dim just as the vessel's walls are dim. And now, just to carry your thoughts forward to the time we shall next meet, let me tell you that it is water which causes the dimness. I will show you that we can make it without difficulty assume the form of a liquid. When we parted, we had just mentioned the word products from the candle. For when a candle burns, we found we were able to get various products from it. There was one substance which was not obtained when the candle was burning properly, which was charcoal or smoke. And there was some other substance that went upwards from the flame, which did not appear as smoke, but took some other form and made part of that general current, which, ascending from the candle upwards, becomes invisible and escapes. There were also other products to mention. You remember that in that rising current, having its origin at the candle, we found that one part was condensable against a cold spoon and another part was incondensable. We will first take the condensable part and examine it, and strange to say, we find that that part of the product is just water, nothing but water. On the last occasion, I spoke of it incidentally, merely saying that water was produced among the condensable products of the candle. But today, I wish to draw your attention to water, that we may examine it carefully, especially in relation to the subject, and also with respect to its general existence on the surface of the globe. Now, having previously arranged an experiment for the purpose of condensing water from the products of the candle, my next point will be to show you that this water, and perhaps one of the best means that I can adopt for showing its presence, is to exhibit a very visible action of water, and then to apply that test to what is collected as a drop at the bottom of the vessel. A small piece of potassium shows the presence of water by lighting up and floating about, burning with a violent flame. You see a drop of water, a condensed product of the candle, hanging from under the surface of the dish. I will show you the potassium has the same action upon it as upon the water in the dish in the experiment we have just tried. I will take a drop upon a glass slide, and when I put the potassium to it, you'll see at once, from it taking fire, that there is water present. Now, that water was produced by the candle. Water is one individual thing. It never changes. We can add to it by careful adjustment for a little while, or we can take it apart and get other things from it. But water as water remains always the same, either in a solid, liquid, or fluid state. And now, to go into the history of this wonderful production of water from combustibles and by combustion, I must first of all tell you that this water may exist in different conditions, and although you may now be acquainted with all its forms, they still require us to give a little attention to them for the present, so that we may perceive how the water, when it goes through its protean changes, is entirely and absolutely the same thing, whether it's produced from a candle, by combustion, or from the rivers or ocean. First of all, water, when at the coldest, is ice. Now, we scientists speak of water as water, whether it be in its liquid or solid or gaseous state. We speak of it chemically as water. Water is a thing compounded of two substances, one of which we have derived from the candle, and the other which we shall find elsewhere. Water may occur as ice. Ice changes back into water when the temperature is raised. Water also changes into steam when it's warmed enough. The water, which I have before me, is in its densest state, and although it changes in condition, in form, and in many other qualities, it still is water. And whether we change it into steam by heat, or whether we alter it into ice by cooling, it increases in volume. In the first case, very largely and wonderfully, and in the second, very strangely and powerfully. For instance, I have this metal bottle into which I've poured a little water into it. I'm converting the water into steam for the purpose of showing you the different volumes which water occupies in its different states of liquid water and water vapor or steam. See what a stream of vapor is issuing from this bottle. You observe that we must have made it quite full of steam to have it sent out in that great quantity. And now, as we can convert the water into steam by heat, we convert it back into liquid water by the application of cold. And if we take a watch glass and hold it over the steam, see how soon it gets damp with water. It will condense until the glass is warm. It condenses the water which is now running down the sides of it. I have here another experiment to show the condensation of water from a vapor state back into a liquid state in the same way as the vapor, one of the products of the candle, was condensed against the bottom of the dish and obtained in the form of water. And to show you how truly and thoroughly these changes take place, I will take this bottle, which is now full of steam, and close the top. We shall see what takes place when we cause this water or steam to return back to the fluid state by cooling it in water. You see what has happened. If I had closed the lid and still kept the heat applied to it, it would have burst the vessel. Yet when the steam returns to the state of liquid water, the bottle collapses, there being a vacuum produced inside by the condensation of the steam. I show you these experiments for the purpose of pointing out that in all these occurrences, there is nothing that changes the water into any other thing. It still remains water. And so the vessel is obliged to give way and is crushed inwards. As in the other case, by the further application of heat, it would have been blown outwards. And what do you think the bulk of that water is when it assumes the vaporous condition? A cubic inch of water will expand to a cubic foot of steam, and on the contrary, the application of cold will contract that large amount of steam into this small quantity of water. Let us now take the case of water changing into ice. We can effect that by cooling the water in a dry ice acetone bath. And I shall do so to show you that when water becomes ice, it changes in volume in an extraordinary way. These bottles are made of cast iron. They're very strong and very thick. I suppose they are each 1/3 of an inch in thickness. I filled this one with water to exclude all air. And I'll screw the plug in tightly. We shall see that when we freeze the water in the vessel, it will not be able to hold the ice, and the expansion within will break it into pieces. No communication will take place, you observe, between the water in the bottle and the ice in the outer bowl, but there will be a conveyance of heat from one to the other. The cold has taken possession of the bottle and its contents. Although the iron was thick, the ice had bursted asunder. You see some ice, partly enclosed by the covering of iron, which is too small for them because the ice is larger in bulk than the water. You know very well that ice floats on water. Why? Because the ice is larger than the quantity of water which can produce it, and therefore the ice weighs the lighter and the water is the heavier. To return to our quiet philosophy. We shall not in future be deceived, therefore, by any changes that are produced in water. Water is the same everywhere, whether produced from the ocean or from the flame of the candle. Where then is the water which we get from a candle? I must anticipate a little and tell you. It evidently comes as to part of it from the candle, but is it within the candle beforehand? No. It is not in the candle, and it is not in the air round about the candle which is necessary for its combustion. It is neither in one nor the other, but it comes from their combined action, apart from the candle, apart from the air. And this we have now to trace so that we may understand thoroughly what is the chemical history of a candle when we have it burning on our table. How shall we get at this? I myself know plenty of ways, but I want you to get at it from the association in your minds of what I've already told you. I think you can see a little in this way. I'll use electricity to pull water to pieces. This power supply makes it as though I were applying heat to cause the water to appear to boil. When we separate or electrolyze water into its parts, we get 2 volumes of one gas and 1 of another. The gases produced are not steam. Steam is condensable into water, and when you lower the temperature of steam, you convert it back into fluid water. As you know, water is liquid at room temperature. Notice that this gas, which I've collected, does not become a liquid. I will take another test and apply it to this gas. If I now apply a light to the mouth of the test tube, it ignites with a slight noise. That tells you that it is not steam. Steam puts out a fire. It does not burn. But you saw that when I had in this test tube burnt, we may obtain this substance equally from water produced from the candle flame as from any other source. Here is a vial full of the same gas. I will show you something most interesting. It is a combustible gas, but it is also less dense than air. Steam will condense. This body will rise in the air and not condense. Suppose I take another vial, empty of all but air. If I examine it with a flame, I shall find that it contains nothing but air. I will now take this vial, full of the gas that I am speaking of, and deal with it as though it were a light body. I will hold both upside down and turn the one up under the other. And now, what does the vial contain that had the gas procured from the steam? You will find it only contains air. But look. Here is the combustible substance which I have poured out of the one vial into the other. It still preserves its quality and condition and independence, and therefore is the more worthy of our consideration as belonging to the products of candle. This is what we get from water, the same substance which is contained in the candle. Let us now trace distinctly the connection between these 2 points. This is hydrogen, a body classed among those things which in chemistry we call elements, because we can get nothing else out of them. A candle is not an elementary body, because we can get carbon out of it. We can get this hydrogen out of it, or at least out of the water which it supplies. And this gas has been so named hydrogen because it is that element which in association with another element generates water. This hydrogen is a very beautiful substance. It is so light that it carries things up. It is far lighter than the atmosphere, and I dare say I can show you this by an experiment. Here is our tank of hydrogen, and here are some soap suds. I have a rubber tube connected with the hydrogen tank, and at the end of it, a plastic pipe. Now, I could blow bubbles with my breath, or blow bubbles by means of the hydrogen. You observe how the bubbles fell downwards when I blew them with my warm breath, but notice the difference when I blow them with hydrogen. It shows you how light this gas must be in order to carry with it not merely the ordinary soap bubble, but the larger portion of a drop hanging to the bottom of it. I can show its lightness in a better way than this. Larger bubbles than these may be so lifted up. Indeed, in former times, balloons used to be filled with this gas. Water also contains oxygen. Oxygen, as you will immediately imagine, exists in the atmosphere. For how should the candle burn to produce water without it? Such a thing would be absolutely impossible and chemically impossible without oxygen. Now, as regards this very property of oxygen supporting combustion, which we may compare to air, I'll take a piece of candle to show it to you in a rough way, and the result will be rough. You see the combustion in air. How will it burn in oxygen? I have here a jar of oxygen for you to compare the action of this gas with that of air. See how brightly and how beautifully it burns. Is it wonderful how great the supporting powers of oxygen are as regards combustion? But it does not affect merely the combustion of hydrogen or carbon or the candle, but it exalts all combustions of the common kind. We must now, for a little while longer, look at it with respect to hydrogen. I'm now about to set fire to oxygen and hydrogen mixed in the proportion in which they occur in water. Here is a vessel of soap bubbles made with 1 volume of oxygen and 2 volumes of hydrogen, exactly the same nature as the gas we obtain from electrolysis. I will take a bubble in my hand, and you will perhaps think I'm acting oddly in this experiment, but it is to show you that we must not always trust to noise and sound, but rather to real facts. This oxygen united with the hydrogen, as you saw by the phenomena, and heard by the sound with the utmost readiness of action, and all its powers were taking up in its neutralization of the qualities of the hydrogen. So now I think you will perceive the whole history of water with reference to oxygen in the air from what we have said before. Why does a piece of potassium decompose water? Because it finds oxygen in the water. What is set free when I put it in the water? It sets free hydrogen, and the hydrogen burns. But the potassium itself combines with oxygen, and this piece of potassium, in taking the water apart, the water you may say derived from the combustion of the candle, takes away the oxygen which the candle took from the air, and so sets the hydrogen free. And even if I take a piece of ice and put a piece of potassium upon it, the beautiful affinities by which the oxygen and the hydrogen are related are such that the ice will absolutely set fire to the potassium. It produces a sort of volcanic action. It will be my place, when next we meet, having pointed out these anomalous actions, to show you that none of these extra and strange effects are met with by us, that none of these strange and injurious actions take place when we are burning not merely a candle, but gas in our homes or fuel in our fireplaces, so long as we confine ourselves within the laws that nature has made for our guidance. We have now seen that we can produce hydrogen and oxygen from the water that we obtained from the candle. Hydrogen, you know, comes from the candle, and oxygen, you believe, comes from the air. But then you have a right to ask me, how is it that the air and the oxygen do not equally well burn the candle? If you remember what happened when I put a jar of oxygen over a piece of candle, you recollect that there was a very different kind of combustion to that which takes place in air. Why is this? It's a very important question, and one I shall endeavor to make you understand. It relates most intimately to the nature of the atmosphere, and it's most important to us. We have several tests for oxygen besides the mere burning of bodies. You've seen a candle burnt in oxygen or in the air, but we have other tests beside these, and I'm about to show you one of them for the purpose of carrying your conviction and your experience further. It's a very curious and useful one. I have here a flask half filled with a solution of potassium hydroxide, glucose, and methylene blue indicator, and filled the rest of the way with oxygen gas. I shake the flask and the oxygen mixes with the solution. What happens, say you? They together produce no such combustion as was seen in the case of the candle, but see how the presence of oxygen is told by its association with these other substances. What a beautiful colored solution I have obtained in this way, showing me the presence of the oxygen. In the same way, we can try this experiment by mixing common air with this solution. Here's another flask containing the same solution, but this time with air above it. I shake this flask and you see the result. The solution turns blue, and that shows me that there's oxygen in the air, the very substance that had been already obtained by us from the water produced by the candle. But then, beyond that, how is it that the candle does not burn in air as well as in oxygen? We will come to that point at once. The solutions react with the gas, and the appearance to the eye is alike in both, and I cannot tell which of these flasks contains oxygen and which contains air, although I know they have been previously filled with these gases. In order to examine whether there is any difference between them, we simply need to wait. Notice how the blue color of the solution fades in this flask, the flask with air. Why is that? Because there is in air, besides oxygen, something else present. The solution left something untouched. There is in fact a gas in air which the solution cannot touch, and this gas is not oxygen and yet is part of the atmosphere. So that is one way of opening out air into the two things of which it's composed. Oxygen, which burns our candles or anything else, and this other substance, nitrogen, which will not burn them. This other part of the air is by far the larger proportion, and it's a very curious body when we come to examine it. It is remarkably curious, and yet you say perhaps that it's very uninteresting. It is uninteresting in some respects because of this, that it shows no brilliant effects of combustion. If I test it with a taper as I do oxygen and hydrogen, it does not burn like hydrogen, nor does it make the taper burn like oxygen. It has no smell, it is not sour, it does not dissolve in water, it is neither an acid nor an alkali. It is as indifferent to all our organs as it is possible for a thing to be. And you might say, it is nothing. It is not worth chemical attention. What does it do in the air? Ah, then come our beautiful and fine results shown us by an observant philosophy. Suppose in place of having nitrogen or nitrogen and oxygen, we had pure oxygen as our atmosphere. What would become of us? A piece of iron lit in a jar of oxygen, for example, goes on burning to the end. When you see a fire in an iron grate, imagine where the grate would go if the whole of the atmosphere were oxygen. The grate would burn up more powerfully than the coals, for the iron of the grate itself is even more combustible than the coals which we burn in it. A fire put into the middle of a locomotive would be a fire in a magazine of fuel if the atmosphere were oxygen. The nitrogen lowers it down and makes it moderate and useful for us, and then with all that, it takes away with it the fumes that you have seen produced from the candle, disperses them throughout the whole of the atmosphere, and carries them away to places where they are wanted to perform a great and glorious purpose of good to humankind for the sustenance of vegetation, and thus does a most wonderful work. Although you say on examining it, why, it is a perfectly indifferent thing. This nitrogen in its ordinary state is an inactive element. No action short of the most intense electric force, and then in the most infinitely small degree, can cause the nitrogen to combine directly with other elements of the atmosphere or with other things round it. It is a perfectly indifferent, and therefore to say, a safe substance. But before I take you to that result, I must tell you about the atmosphere itself. Here is a composition of 100 parts of atmospheric air. It is a true analysis of the atmosphere, so far as regards the quantity of oxygen and the quantity of nitrogen present. By our analysis, we find that 5 liters of the atmosphere contains only 1 liter of oxygen and 4 liters of nitrogen by bulk. That is our analysis of the atmosphere. It requires all that quantity of nitrogen to reduce the oxygen down so as to be able to supply the candle properly with fuel, so as to supply us with an atmosphere which our lungs can healthily and safely breathe. For it is just as important to make the oxygen right for us to breathe as it is to make the atmosphere right for the burning of the fire and the candle. First of all, let me tell you the weight of these gases. 2 liters of nitrogen weighs roughly 2.29 grams. The oxygen is heavier. 2 liters of it weigh about 2.62 grams. 2 liters of air weigh about 2.37 grams. You might ask, how do you weigh gases? I will show you. It's very simple and easily done. Here is a balance, and here is a plastic bottle. This bottle is balanced by the weight of the other bottle. And here is a pump by which we can force the air into the bottle, and with it we will force in a certain number of volumes of air. Now, see how it sinks? It is much heavier than it was. By what? By the air that we have forced into it by the pump. There's not a greater volume of air, but there is the same volume of heavier air because we have forced in air upon it. This bulk of air weighs about 2.5 grams. It is wonderful how it accumulates when you come to larger volumes. I have calculated the weight of air in this room, and you would hardly imagine it, but it is above a ton. So rapidly do the weights rise up, and so important is the presence of the atmosphere, and of the oxygen and the nitrogen in it, and the use it performs in conveying things to and fro from place to place, and carrying bad vapors to places where they will do good instead of harm. Having given you that little illustration with respect to the weight of the air, let me show you certain consequences of it. When I put my finger on this tube and remove the air, look at what happens. Why is my finger fastened to this tube, and why am I able to pull the hose about? It is the weight of the air that is above. I have another experiment here which I think will explain to you more about it. When air is pumped from underneath the plastic, which is stretched over the funnel, you will see the effect in another shape. The top is quite flat at present, but I will make a very little motion with the pump, and now look at it. See how it has gone down, and see how it's bent in? You will see the plastic go in more and more until at last I expect it will be driven in and broken by the force of the atmosphere pressing upon it. Now, that was done entirely by the weight of the air pressing on it, and you can easily understand how that is. The particles that are piled up in the atmosphere stand upon each other as these 5 cubes do. You can easily conceive that 4 of these 5 cubes are resting upon the bottom one, and if I take that away, the others will all sink down. So it is with the atmosphere. The air that is above is sustained by the air that is beneath, and when the air is pumped away from beneath them, the change occurs which you saw when I placed my finger on the air pump, and which you saw in the case of the plastic, and which you shall see better in the next demonstration. It's a little apparatus of 2 hollow plastic hemispheres closely fitted together and having an outlet through which we can exhaust the air from the inside. And although the 2 halves are so easily taken apart while the air is left within, yet you will see when we exhaust it by and by, I'll be unable to pull them apart. Every square inch of surface that is contained in the area of this vessel sustains 15 pounds by weight, or nearly so, when the air is taken out. Here is another very pretty thing, a suction cup. If I clamp it upon the glass, you can see at once it holds. I can easily slip it about, and if I pull it up, it pulls the glass plate with it. Only when I lift the edge can I get it off. Why does it hold? It is only kept down by the pressure of the atmosphere above. I have a second one, and if I press them together, you'll see how firmly they stick. And indeed, we may use them as they are proposed to be used, to stick against windows or against walls, where they will adhere for an evening and serve to hang anything on them that you want. Next is an experiment that you can do at home. It is a very pretty illustration of the pressure of the atmosphere. The pop gun will confine the air that is within the tube perfectly and completely for our purpose. The confined air will drive the front ball out with a force something like that of gunpowder, for gunpowder is in part dependent upon the same action as this pop gun. I saw the other day an experiment which pleased me much, as I thought it would serve our purpose here. By the proper application of air, I expect to be able to drive this egg out of one cup into the other by the force of my breath. But if I fail, it's in a good cause, and I do not promise success because I've been talking more than I ought to make the experiment succeed. You see that the air which I blew went downward between the egg and the cup and made a blast under the egg, and is thus able to lift a heavy thing. For a full egg is a very heavy thing for air to lift. If you want to make the experiment, you had better boil the egg quite hard first, and then you may very safely try to blow it from one cup to the other with a little care. I have now kept you long enough upon this property of the weight of the air, but there's another thing I should like to mention. You saw the way in which the pop gun, I was able to drive the second yellow ball a half or 2/3 of an inch before the first ball started by virtue of the elasticity of the air. Just as I pressed into the plastic bottle the particles of air by means of a pump, now this depends upon a wonderful property in the air, namely its compressibility. And I should like to give you a good demonstration of this. If I take anything that confines the air properly, as does this balloon, which also is able to contract and expand so as to give us a measure of the elasticity of the air, and confine in the balloon a certain portion of air, and then if we take the atmosphere off with this pump, just as in the cases we put the pressure on, if we take the pressure off, you will see how it will then go on expanding and expanding larger and larger until it will fill the whole of this jar. We will now turn to another very important part of our subject, remembering that we have examined the candle in its burning and have found that it gives rise to various products. We have the products you know of soot, of water, and of something else which you have not yet examined. We have collected the water, but have allowed the other things to go into the air. Let us now examine some of these other products. Here is an experiment which I think will help you in part in this way. First, we put our candle under a chimney. My candle will go on burning because the air passage is open at the bottom and at the top. You see the moisture appearing, that you already know about. It is water produced from the candle by the action of the air upon the hydrogen. But besides that, something is going out at the top. It is not moisture, it's not water, it is not condensable, and yet, after all, it has very singular properties. You will find that the gas coming out of the top of our chimney is nearly sufficient to blow the light out I'm holding to it. And if I put the light fairly opposed to the current, it will blow it quite out. You will say that that is as it should be, because the nitrogen does not support combustion and ought to put the match out, since the match will not burn in nitrogen. But is there nothing else there than nitrogen? I must now anticipate. That is to say, I must use my own knowledge to supply you with the means that we adopt for the purpose of ascertaining these things and examining such gases as these. If I hold an empty flask to this chimney, I shall capture the combustion of the candle below. We shall soon find that this flask contains not merely a gas that is bad as regards the combustion of a taper put into it, but having other properties. If I take some of this beautiful, clear lime water and pour it into this flask which has collected the gas from the candle, you will see a change come about. You see that the water has become quite milky. Observe, this will not happen with air merely. Here is a flask filled with air, and if I put a little lime water into it, neither the oxygen, nor the nitrogen, nor anything else that is in that quantity of air will make any change in the lime water. It remains perfectly clear, and no shaking of that quantity of lime water with that quantity of air in its common state will cause any change. This is chalk consisting of the lime in the lime water combined with something that came from the candle. That other product which we are in search of and which I want to tell you about today. This is a substance made visible to us by its action, which is not the action of the lime water either upon the oxygen or upon the nitrogen, nor upon the water itself, but it is something new to us from the candle. But we have a better means of getting the substance and in greater quantity so as to ascertain what its general characteristics are. We can produce this substance in great abundance from a multitude of unexpected sources. All limestones can produce a great deal of this gas, which issues from the candle, and which we call carbon dioxide. All chalks, all shells, all corals can also make a great quantity of this curious gas. We can easily evolve carbon dioxide from marble. Here is a jar containing some hydrochloric acid, and here's a taper which, if I put it into that jar, will show only the presence of common air. There is, you see, pure air down to the bottom. The jar is full of it. Here is a substance, marble, a very beautiful and superior marble, and if I put that piece into the jar, a great boiling apparently goes on. That, however, is not steam. It is a gas that is rising up. And if I now search the jar by a taper, I shall have exactly the same effect produced upon the taper as I had from the gas which issued from the end of the chimney over the burning candle. It is exactly the same action and caused by the very same substance that issued from the candle. And in this way, we can get carbon dioxide in great abundance. We have already nearly filled the jar. We also find that this gas is not merely contained in marble. Here is some common chalk, and in this flask, more hydrochloric acid. It too evolves carbon dioxide, exactly the same in its nature and properties as the gas we obtain from the combustion of the candle in the atmosphere. And no matter how different the methods, from marble or chalk or candle, by which we prepare this carbon dioxide, you will see when we get to the end of our subject that it is all exactly the same whether prepared in the one way or another. We will now proceed to the next experiment with regard to carbon dioxide. What is its nature? Here is a vessel full of carbon dioxide, and we will try it, as we have done in so many other gases, by combustion. You see, it is not combustible, nor does it support combustion. Neither, as we know, does it dissolve much in water, because we collect it over water very easily. Then you know that it has an effect and becomes white in contact with lime water. And when it does become white in that way, it becomes one of the constituents to make carbonate of lime or limestone. It is a very weighty gas. It is heavier than the atmosphere. I have put their respective weights at the lower part of this table, along with, for comparison, the weights of the other gases we've been examining. 2 liters of this weighs about 3.6 grams. You can see by some experiments that this is a heavy gas. I have a flask containing dry ice that is subliming and thus pushing out the air, replacing it with carbon dioxide. I'll pour a little of this carbon dioxide into another flask filled with nothing but air. I wonder whether any has gone in or not. I cannot tell by the appearance, but I can in this way. It extinguishes the flame. If I were to examine it by lime water, I would find it by that test also. Next is an experiment where I will show you its density. If I blow soap bubbles, which of course are filled with air, into this container filled with carbon dioxide, they will float. They are floating by virtue of the greater density of the carbon dioxide than of the air. And now, having so far given you the history of carbon dioxide as to its sources in the candle, as to its physical properties and density, in the next lecture I shall show you of what it is composed and where it gets its elements from. I told you when we last met a good deal about carbon dioxide. We found by the lime water tests that when the vapor from the top of the candle was received into bottles and tested by a solution of lime water, the composition of which I explained to you and which you can make for yourselves, we had that the white opacity, which was in fact calcareous matter like shells and corals and many of the rocks and minerals in the earth. But I had not yet told you fully and clearly the chemical history of this substance, carbon dioxide, as we have it from the candle, and I must now resume that subject. We have seen the products and the nature of them as they issue from the candle. We have traced the water to its elements, and now we have to see where are the elements of the carbon dioxide supplied by the candle. A few experiments will show you this. You remember that when a candle burns badly, it produces smoke. But if it is burning well, there is no smoke. And you know that the brightness of the candle is due to the smoke, which becomes ignited. Here is an experiment to prove this. So long as the smoke remains in the flame of the candle and becomes ignited, it gives a beautiful light and never appears to us in the form of black particles. I will light some fuel, which is extravagant in its burning. This will serve our purpose, a little lighter fluid on a sponge. You see the smoke rising from it and floating into the air in large quantities. And remember now, the carbon dioxide that we have from the candle is from such smoke as that. To make that evident to you, I will introduce this into a container where I have plenty of oxygen, the rich part of the atmosphere. You now see that the smoke is all consumed. The carbon which you saw flying off from the lighter fluid flame in the air is now entirely burned in this oxygen, exactly as in the combustion of the candle. All the carbon which is burned in oxygen or air comes out as carbon dioxide, while those particles which are not so burned show you the second substance in the carbon dioxide, namely the carbon, that body which made the flame so bright while there was plenty of air, but which was thrown off in excess when there was not oxygen enough to burn it. There is another experiment which I must give you before you are fully acquainted with the general nature of carbon dioxide. Being a compound body consisting of carbon and oxygen, carbon dioxide is a body that we ought to be able to take asunder, and so we can. As we did with water, so we can with carbon dioxide, take the two parts asunder. The simplest and quickest way is to act upon the carbon dioxide by a substance that can attract the oxygen from it and leave the carbon behind. You recollect that I took potassium and put it upon water or ice, and you saw that it could take the oxygen from the hydrogen. Now, suppose we do something of the same kind here with this carbon dioxide. Now, let me take some magnesium turnings and get them to act upon carbon dioxide in the form of dry ice. If we apply heat to the magnesium, you will see that it can burn in carbon dioxide, and its very burning is proof of the existence of oxygen in the carbon dioxide. In addition to a brilliant light, you will see what is left behind. we find that besides the white powder formed, which is magnesium oxide, there's a quantity of carbon produced, carbon obtained from the carbon dioxide as a common black substance, so that you have the entire proof of the nature of carbon dioxide as consisting of carbon and oxygen. And now, I may tell you that whenever carbon burns under common circumstances, it produces carbon dioxide. Suppose I take this piece of wood and put it in a bottle with lime water. I might shake that water up with wood and the atmosphere as long as I pleased. It would still remain clear as you see it. But suppose I burn the piece of wood in the air of that bottle. You of course know that I get water. Do I get carbon dioxide? There it is, the carbonate lime which results from carbon dioxide, and that carbon dioxide must be formed from the carbon which comes from the wood, from the candle, or any other thing. Indeed, you have yourselves tried a very pretty experiment by which you see the carbon in wood. If you take a piece of wood and partly burn it and then blow it out, you have carbon left. Here is the piece of wood that I partly burnt. You see the carbon left on it. A candle does not show it, nor does a Bunsen burner, but both contain carbon. You see no carbon when they burn, but you see a flame, and because it is bright, it will lead you to guess that there's carbon in the flame. I hope that by these experiments you will learn to see when carbon is present and understand what are the products of combustion when gas or other bodies are thoroughly burned in the air. Before we leave the subject of carbon, let us make a few experiments and remarks upon its wonderful condition as respects ordinary combustion. I have shown you that the carbon in burning burns only as a solid body, and yet you'll perceive that after it is burned, it ceases to be a solid. There are very few fuels that act like this. It is in fact only that great source of fuel, the carbonaceous series, the coals, charcoals, and woods that can do it. I do not know that there is any other elementary substance besides carbon that burns with these conditions. And if it had been so, what would happen to us? Suppose all fuel had been like iron, which, when it burns, burns into a solid substance. We could not then have such a combustion as you have in a fireplace. Now, I must take you to a very interesting part of our subject, to the relation between the combustion of a candle and that living kind of combustion which goes on within us. In every one of us, there's a living process of combustion going on very similar to that of a candle. And I must try to make that plain to you. For it is not merely true in a poetical sense, the relation of the life of humans to a candle, and if you follow, I think I can make this clear. In order to make the relation very plain, I've devised a little apparatus with an air inlet at the bottom, and I'll limit the airflow out of the top with this wire mesh. The lighted candle goes on, you see, burning very well. You observe that the air which feeds the flame goes along the horizontal tube and ascends the vessel. If I stop the aperture through which the air flows, I stop combustion, as you will perceive. I stop the supply of air, and consequently the candle goes out. But now, what will you think of this fact? In a former experiment, I showed you the gaseous products coming from one burning candle to a flame. If I take the vapor proceeding from another candle and send it through this tube, I should put this burning candle out. But what will you say when I tell you that my breath will put out that candle? I do not mean by blowing it out, but simply that the nature of my breath is such that a candle cannot burn in it. I will exhale, and without blowing the flame in any way, let no air enter the tube but what comes from my mouth. You see the result. I did not blow the candle out, I merely let the air which I expired pass into the aperture, and the result was that the light went out for want of oxygen and for no other reason. My lungs had taken the oxygen out of the air, and there was no more to supply the combustion of the candle. It is, I think, very pretty to see the time it takes before the bad air which I throw into this part of the apparatus has reached the candle. The candle at first goes on burning, but so soon as the air has had time to reach it, it goes out. To pursue this a little further, let us see what will happen with lime water. Here is a flask which contains a little lime water and is so arranged as regard the pipes as to give access to the air within so that we can ascertain the effect of respired or unrespired air upon it. Of course, I can either draw air in here and so make the air that feeds my lungs go through the lime water, or I can force the air out of my lungs through this tube which goes to the bottom and so shows its effect upon the lime water. You will observe that, however long I draw the external air into the lime water and then through it to my lungs, I shall produce no effect upon the water. It does not make the lime water turbid, but if I throw the air from my lungs through the lime water several times in succession, you will see how white and milky the water is getting, showing the effect which expired air has upon it. And now you begin to know that the atmosphere, which we have spoiled by respiration, is spoiled by carbon dioxide, and you see it here in contact with the lime water. Let us now go a little further. What is all this process going on within us which we cannot do without, either day or night? If we restrain our respiration, as we can to a certain extent, we should destroy ourselves. When we are asleep, the organs of respiration and the parts that are associated with them still go on with their action. So necessary is this process of respiration to us, this contact of the air with the lungs. I must tell you, in the briefest possible manner, what this process is. We consume food. The food goes through that strange set of vessels and organs within us and is brought into various parts of the body, into the digestive parts especially. The air that we inhale is drawn into the lungs, absorbed into the bloodstream, and transported throughout the body so that the oxygen and the food come close together. In the body, a curious, wonderful change takes place. The oxygen combines with the carbon, not carbon in a free state, but is in this case placed ready for action at the moment, and makes carbon dioxide, and is so thrown out into the atmosphere, and thus the singular result takes place. The oxygen can thus act upon the food, producing precisely the same results in kind as we have seen in the case of the candle. The candle combines with parts of the air, forming carbon dioxide, and evolves heat. We may thus look upon the food as fuel. Let us consider sugar, which will serve my purpose. It is a compound of carbon, hydrogen, and oxygen, similar to a candle, as containing the same elements, although not in the same proportion, the proportions being as shown in this table. This is indeed a very curious thing, which you can well remember, for the oxygen and hydrogen are in exactly the proportions which form water, so that sugar may be said to be compounded of 72 parts of carbon and 99 parts of water. And it is the carbon in the sugar that combines with the oxygen carried in the air by the process of respiration, so making us like candles, producing these actions, warmth, and far more wonderful results besides, for the sustenance of the system by a most beautiful and simple process. To make this still more striking, let me show you an experiment with a bit of sugar. If I put some sulfuric acid on sugar, it takes away the water and leaves the carbon in a black mass. You see how the carbon is coming out, and before long we shall have a solid mass of charcoal, all of which has come out of the sugar. Sugar, as you know, is food, and here we have absolutely a solid lump of carbon where you would not have expected it. Recall that I oxidized sugar in an earlier lecture using potassium chloride, which is a quicker one than the atmosphere, and different from respiration in its form, though not different in its kind. What occurs in my lungs, taking in oxygen from another source, namely the atmosphere, takes place between potassium chlorite and sugar by a more rapid process. I also showed you how potassium reacted with water. The moment the potassium was brought to the water, it acted. What a beautiful instance of chemical affinity by which all our operations proceed. When we breathe, the same operation is going on within us. When we burn a candle, the attraction of the different parts one to the other is going on. We have this difference between charcoal and potassium that, well, the potassium can start into action at once. If there be access of water to it, the carbon will remain days, weeks, months, or years in the presence of air. The manuscripts of Herculaneum were written with carbonaceous ink, and there they have been for almost 2,000 years, not having been at all changed by the atmosphere, though coming in contact with it under various circumstances. Now, what is the circumstance which makes the potassium and carbon differ in this respect? It is a striking thing to see that the matter which is appointed to serve the purpose of fuel waits in its action. It does not start off burning like the potassium. The carbon waits for action. This waiting is a curious and wonderful thing. Candles do not start into action at once like the potassium, but there they wait for years, perhaps for ages, without undergoing any alteration. It is curious to see how different substances wait, how some will wait till the temperature is raised a little, and others till it is raised a good deal. I have here a little gunpowder and some gun cotton. Even these things differ in the conditions under which they will burn. The gunpowder is composed of carbon and other substances, making it highly combustible, and the gun cotton is another combustible preparation. They are both waiting, but they will start into activity at different degrees of heat or under different conditions. By applying a heated glass rod to them, we shall see which will start first. You see the gun cotton has gone off, but not even the hottest part of the rod is now hot enough to fire the gunpowder. How beautifully that shows you the differences in the degree in which bodies act in this way. In the one case, the substances will wait any time until the associated bodies are made active by heat, but in the other, as in the process of respiration, it waits no time. The air that enters when we breathe unites with the carbon. Even in the lowest temperatures which the body can bear short of being frozen, the action begins at once, producing the carbon dioxide of respiration, and so all things go on fitly and properly. You will be astonished when I tell you what this curious play of carbon amounts to. A candle will burn some 4, 5, 6, or 7 hours. What then must be the daily amount of carbon going up into the air in the way of carbon dioxide? What a quantity of carbon must go from each of us in respiration. What a wonderful change of carbon must take place under these circumstances of combustion or respiration. A person in 24 hours converts as much as 200 grams of carbon into carbon dioxide. A dairy cow will convert 2,000 grams and a horse 2,200 solely by the act of respiration. That is, the horse in 24 hours burns 2,200 grams of charcoal or carbon in his organs of respiration to supply his natural warmth in that time. All the warm-blooded animals get their warmth in this way, by the conversion of carbon, not in a free state, but in a state of combination. And what an extraordinary notion this gives us of the alterations going on in our atmosphere. As much as 1.5 million tons of carbon dioxide is formed by human respiration in the world in 24 hours. And where does all this go? Up into the air. If the carbon had been like iron, which in burning produces a solid substance, what would happen? Combustion could not go on. As charcoal burns, it becomes a vapor and passes off into the atmosphere, which is the great vehicle, the great carrier for conveying it away to other places. Then what becomes of it? Wonderful it is to find the change produced by respiration, which seems so injurious to us, for we cannot breathe air twice over, is the very life and support of plants and vegetables that grow upon the surface of the earth. It is the same also under the surface, in the great bodies of water. For fishes and other animals respire upon the same principle, though not exactly by contact with the open air. Fish respire by the oxygen which is dissolved from the air by the water and form carbon dioxide. And they all move about to produce the one great work of making the animal and vegetable kingdom subservient to each other. And all the plants growing upon the surface of the earth absorb carbon. These leaves are taking up their carbon from the atmosphere, to which we have given it in the form of carbon dioxide, and they are growing and prospering. Give them a pure air like ours, and they could not live in it. Give them carbon with other matter, and they live and rejoice. This tree, as do all plants, gets its carbon from the atmosphere, which, as we have seen, carries away what is bad for us and at the same time good for them. What is disease to the one, being health to the other. So are we made dependent not merely upon our fellow creatures, but upon our fellow existers, all nature being tied together by the laws that make one part conduce to the good of another. Indeed, all I can say to you at the end of these lectures, for we must come to an end at one time or other, is to express a wish that you may, in your generation, be fit to compare to a candle, that you may, like it, shine as lights to those about you, that in all your actions you may justify the beauty of the taper by making your deeds honorable and effectual in the discharge of your duty to humankind.